This is a video solution for problem 6 on homework 5. We are given a uniform, we're given a line load. It's not a uniform load. It's decreasing in value from left to right. It has a peak intensity of 7 kips per foot, and it has a lower intensity of 2 kips per foot. And we're asked to convert it into a single resultant force and report the distance x bar at which the force will act. This is an equivalent systems problem. I'm going to do a copy paste of the image and put it over here. As you're learning these, I find that students do better with some clear labeling. So call this one system 1, call this one system 2. If they're equivalent, then the summation of forces in the y direction in system 1 matches the summation of forces in the y direction system 2. The summation of moments about some axis 1 matches the summation of moments about the same axis in system 2. So in order to make some headway on this problem, I'm going to choose to split up that function into 2 pieces. So I'm going to do this. I'm going to take this rectangular piece, which is a uniform load, a constant load of 2 kips per foot over the 13 feet. I'm going to turn that into one resultant force right at the middle here. So I'm going to have, I'll call that FR1. That's due to the rectangle. And then the remaining piece of the load, which is a triangle, and the triangle is going to have a height of 7 minus 2 equals 5 kips per foot, and then a base of 13 feet. When I integrate that load, I'm going to place it at the third point of the triangle. So I'm going to have another force here, F sub R sub 2, and F sub R, bleh, a tongue twister, F sub R sub 1, that one I know is located half of 13 from our origin. And F sub R sub 2, that one I know is equal to 13 thirds feet from our origin. Okay, let us work through our equations. So the first one is our equivalency with respect to y direction forces. Up a little bit more real estate here. That again. Oh, that's why. 2, 3, 4, 5. How about that? Okay. Switch over to purple for no good reason. Okay. So let's do my summation of forces in the y direction in system 1 is equal to FR1 plus FR2. FR1, the rectangle, so I do base times height. My base is 13 feet. My height is 2 kips per foot. And maybe I'm going to do it this way since I'm teaching. So I'm going to do 13 feet just to emphasize that we're going to come out and cancel that. Okay, so we've got 13 times 2 kips for that one. And then plus F sub R sub 2. So my height of the triangle is 5 kips per foot. The base of the triangle is 13 feet. And then I need to remember to divide by 2. Okay, so if we just were to simplify this, then F sub R sub 1 is 13 times 2, 26 kips. And 5/13 divided by 2 5 times 13 divided by 2, so 32.5 kips. Okay, and I'll just make a little note to myself right up here. F sub r sub 1, 26 kips. F sub r sub 2, 32.5 kips. The first part of the problem asks me for how much that force is. And so here, I just need to sum these two up. 6 and 2 is 8. 2 and 3 is 5. So it should be 58.5 kips. And, a kip is 1,000 pounds. So that can also be expressed as 58.5 E3 pounds. If you wanted to do that conversion back from kips to pounds, it would look something. Okay, so that's the first part. That is what, and I mean, honestly, what I'm doing here is really I'm creating 3 equivalent systems. Let me make sure that's clear. So I'm doing the 2 forces as an intermediate step. And then my final resultant force, when I just calculated 58.5, is at some distance, and we haven't solved for that yet. All right, so far we've deduced that total magnitude, and now we're ready to figure out some distances. Right, I'll switch over to green. So I want to use this moment summation. So this is a static equivalency. So it means the tendency to rotate about axis in system 1 matches the tendency to rotate in system 2. And in our case, right, it also matches the tendency to rotate about the same axis in system 3. And so I'm going to look here at systems 2 versus 3, and I'm thinking the origin, actually it's labeled at A, so I'll stick with A. So the origin or point A, whatever you want to call it, this fiber over here on the left, it makes sense to some moments about that because this is what I want to solve for, this distance, and it's going to be hardwired into that equation really, really nicely. So let's go ahead and do it. So we're going to execute this operation. So on the left side, the summation of moments about A in system 2. So I've got 32.5 kips at a distance of 13/3 feet. And that sign, that tendency to rotate about A, is going to be clockwise, thumbs down, negative. Next term, I've got my 26 kips. And its distance away is 6.5 feet. That's the moment arm. And it is also negative clockwise with respect to rotation about A. And those are the only 2 terms. We're not setting this equal to 0 because it's not an equilibrium problem. We're talking about equivalency. And on the right side of the equation, now I just execute this. So I've got 1 term in the equation. It's 58.5. The distance is what I'm looking for. That's x bar. And the sign is clockwise. Negative thumbs down for that. All right. All the kips cancel out. So my calculator operation is now, oh, and I'm going to divide also, I'm going to divide everything by -1. So it's going to result in this calculation. 32.5 times 13 divided by 3 plus 26 times 6.5 equals, let's see, all of that divided by 58.5. 5. And this is going to be feet equals x bar. Just double check that since I'm mathing live and prone to mistakes when I'm doing that. Okay, that makes sense. All right, let's do find the calculator and let's punch it through. All right, so 32.5 times 13 divided by 3 equals plus 26 times 6.5 equals all over 58.5 equals, and I get an answer of 5.296. 5.296. So to 3 sig figs, 5.30 would be the best answer. Okay, so that is our equivalent system. We can take this input and replace it with this force precisely located at that location and use that instead of the intermediate steps. That's it for this one.